Chapter 8. We have seen that the elements are classified into metals and non-metals. Let us study their properties in detail in the chapter Understanding Metals and Non-Metals. Earth is an abundant source of material. The air we breathe, the water we drink, stones, rocks, almost everything that is around us is useful for some purpose or the other. Most of these materials are the compounds of some or the other elements, while some of the substances are found in their elemental form. For convenience, these elements have been classified into metals, non-metals, and metalloids. Metalloids are the elements which possess both the properties of metals as well as non-metals. Example: silicon, germanium, antimony, etc. Whereas metals and non-metals are classified distinctly by their physical and chemical properties. Let us look at one activity. Take sample pieces of copper, iron, aluminium, charcoal, sulfur powder, pencil lead, that is graphite. Identify and classify the above samples as metals and non-metals. Copper, iron, and aluminium are metals. Charcoal, sulfur powder, and pencil lead, that is graphite, are non-metals. Which features did you consider to classify them? Hardness, luster, sonorous, that ringing sound when struck. Metals are hard, they shine, and are sonorous. Non-metals are brittle, they look dull, and are not sonorous. Now let us move to the physical properties of metals. Physical state. Metals are solids at room temperature, with exception of mercury and gallium, which are in liquid form at room temperature. Let us perform an activity. Take samples of metals like iron, copper, aluminium, and magnesium. Note the appearance of each sample. We find that all metals shine in natural state. Clean the surface of each sample with sandpaper and note their appearance again. When polished, it has a reflecting surface. It is a luster. Metals in their pure state have a shine and can be polished to give a highly reflective surface. Again, activity time. Take a lid of a cold drink bottle, a coin, a thick aluminium wire. Strike it with a hammer several times. What do you observe? Record the change in shapes of the metals. All things become flat like a sheet. This property is called as malleability. You will find that metals have the ability to withstand hammering and can be made into thin sheets. Students, you all must have seen your mother's sari with a zari border. Observe the zari borders of pure silk saris. Do you know what this zari is made up of? And why do you think intricate designs with zari can be woven in a sari? Zari is made from silver and gold drawn into thread. These threads help in making intricate designs. Students, take an electric wire. Remove the insulation of an electric wire. What do you observe? We can see the copper wire inside the insulation. The ability of metals to be drawn into thin wires is called ductility. Gold and silver are the most ductile metals. You will be surprised to know that 1 gram of gold can be drawn into a wire of 2 kilometers length. Students, name some metals that are used for making cooking vessels. Iron, aluminium, copper, and stainless steel are some metals that are used for making cooking vessels. Do you know why only these metals are used for making cooking vessels? All these metals are good conductors of heat. Let us look at another activity. Take an aluminium or copper wire. Clamp this wire on a stand as shown in the figure. Keep a wedge of butter on the free end of the wire. Heat the wire with a spirit lamp or a burner near the place where it is clamped. Does the metal wire melt? No. Note your observations. The butter starts melting after some time. From this, we can say that metals are good conductors of heat and have high melting points. Silver and copper are the best conductors of heat, whereas lead and mercury are the poor conductors of heat. Let us perform one activity before moving to the next property. Set up an electrical circuit as shown. Place the metal to be tested in the circuit between the terminals. Does the bulb glow? Yes. What does this indicate? It indicates that aluminium is a good conductor of electricity. Now look at this electric wire. What is the inside and outside material of an electric wire? Copper wire is inside. It is covered with PVC, that is, polyvinyl chloride. This shows that metals are good conductors of electricity. Electric wires are made of copper having an outer coating of PVC, that is, polyvinyl chloride, since PVC is a bad conductor of electricity. Let us understand the next property through this activity. Take samples of iron nail, thick copper and aluminium wire and magnesium ribbon. Take a piece of sodium metal in a watch glass. Students, handle sodium metal carefully. Try to cut these samples with a sharp knife and note your observations. All metals cannot be cut with a knife. Since sodium is a soft metal, it can be cut easily with a knife. This shows that metals are generally hard and the hardness differs from metal to metal. Alkali metals like sodium and potassium are soft metals and can be cut easily with a knife. Let us study about another property, that is melting point and boiling point. Metals usually have high melting and boiling point. Tungsten has the highest melting point, whereas sodium and potassium have low melting points. Students, have you ever thought why the bells in your schools, temples, and churches are made of metals? Metals are sonorous, so they are used in making bells. Sonorous means the metals which can produce a sound on striking a hard surface. Let us perform this activity before moving to the physical properties of non-metals. Take the samples of coal, graphite, sulfur, iodine and bromine. We will note the physical properties like physical state, luster, malleability, ductility, conduction of heat, conduction of electricity, melting point and boiling point, sonorous of these non-metals. Physical state. Coal, graphite, sulfur, iodine are solid and bromine is in liquid state. Luster. Coal, graphite, sulfur, iodine don't shine. Only bromine has luster. Malleability and ductility. They are neither malleable nor ductile. Conduction of heat and electricity. Graphite is a good conductor of heat and electricity. Other non-metals are bad conductors of heat and electricity. All of them have low melting and boiling points. All of them are not sonorous. Let us look at the physical properties of non-metals. Non-metals are either in solid or gaseous state, with the exception of bromine, which is in liquid state. Non-metals usually do not have luster, except iodine and diamond, which is an allotrope of carbon and the most lustrous of all the substances. Non-metals do not possess the property of hardness except carbon in the form of diamond, which is the hardest substance known. Diamond also has a high melting and boiling point. Non-metals do not conduct electricity except graphite, which is an allotrope of carbon. Since there are exceptions in each of the physical properties, elements can be classified more clearly as metals and non-metals on the basis of their chemical properties. Now let us move on to the chemical properties of metals. To learn about the chemical properties of metals, take samples of aluminium, copper, iron, lead, magnesium, zinc and sodium to do this activity. Hold any of the samples taken above with a pair of tongs and burn over a flame. Repeat with the other metal samples except sodium. Hold samples with a pair of tongs and burn over a flame. Collect the product formed. Let the product and the metal surface cool down. Which metals burn easily? Sodium burns in air. Magnesium burns on heating. Aluminium, copper, iron, lead and zinc do not burn easily. How does the metal surface appear after burning? Metal surface turns black on heating. Are the products soluble in water? Only sodium oxide is soluble in water. Other products are not soluble in water. Let us look at the reaction of metals with oxygen. Almost all metals react with oxygen to form metal oxide, but the reactivity differs for different metals. Sodium and potassium are the most reactive metals. Sodium reacts with oxygen in air at room temperature to form sodium oxide. Hence, sodium is stored under kerosene oil to prevent its reaction with oxygen, moisture and carbon dioxide. 4Na plus O2 gives 2Na2O. Most metal oxides are insoluble in water, but some of these dissolve in water to form alkalis. Example: sodium oxide and potassium oxide dissolve in water to produce alkalis as follows. Na2O plus H2O gives 2NaOH. K2O plus H2O gives 2KOH. Magnesium does not react with oxygen at room temperature, but on heating, magnesium burns in air with intense light and heat to form magnesium oxide. 2Mg plus O2 on heating gives 2MgO. Zinc burns in air only on strong heating to form zinc oxide. 2Zn plus O2 on heating gives 2ZnO. Iron does not burn even on strong heating, but iron filings burn vigorously when sprinkled in the flame of the burner. 3Fe plus 2O2 on heating gives Fe3O4. Copper is least reactive and it does not burn, but on heating the hot metal is coated with a black colored layer of copper oxide. 2Cu plus O2 on heating gives 2CuO. Aluminium develops a thin oxide layer when exposed to air. 4Al plus 3O2 gives 2Al2O3. Now let us try to understand the term anodized panels. Anodizing is a process of forming a thick oxide layer of aluminium. Aluminium develops a thin oxide layer when exposed to air. This aluminium oxide coat makes it resistant to further corrosion. The resistance can be improved by making the oxide layer thicker. In this technique, aluminium article is used as an anode. Electrolyte used is dilute sulfuric acid. The anode reaction results in formation of a black-colored thin film of aluminium oxide on the surface of anode. By putting appropriate dyes in the electrolytic bath, colored surface with decorative finish can be achieved. Kitchen articles like anodized pressure cookers, anodized pans, and also frames of sliding windows are the applications of anodizing techniques. Metal oxides are usually basic in nature, but some metal oxides, such as aluminium oxide and zinc oxide, react with both acids as well as bases to produce salt and water. Hence, they are called as amphoteric oxides. Al2O3 plus 6HCl gives 2AlCl3 plus 3H2O. Aluminium oxide reacts with acid to form salt and water, hence it is a basic oxide. Al2O3 plus 2NaOH gives 2NaAlO2, that is sodium aluminate plus H2O. Here it reacts with a base to give salt and water, hence it behaves like an acidic oxide. Let us see how metals react with water. Let us look at the activity. Take the samples of sodium, potassium, calcium, magnesium, aluminium, iron, zinc to perform the activities given below. Put some pieces of samples taken separately in beakers, half filled with cold water. Which metals react with cold water? Potassium, sodium, and calcium reacted with cold water. Did any metal catch fire in water? Potassium and sodium catch fire when immersed in water. Does any metal start floating after some time? Yes, calcium starts floating. Metals like potassium and sodium react vigorously with cold water. Sodium reacts with water to evolve hydrogen, which immediately catches fire, producing a lot of heat. This is an exothermic reaction. 2K plus 2H2O gives 2KOH plus H2 gas is evolved plus heat energy. 2Na plus 2H2O gives NaOH plus H2 gas is evolved plus heat energy. Calcium reacts with water less vigorously, hence the heat evolved is not sufficient for hydrogen to catch fire. Instead, calcium starts floating because the bubbles of hydrogen gas formed stick to the surface of the metal. Ca plus 2H2O gives CaOH twice plus H2 gas is evolved. Put the metals that did not react with cold water in beakers half filled with hot water. Note your observations. Magnesium reacts with hot water to form magnesium hydroxide and hydrogen. Magnesium also starts floating since the bubbles of hydrogen gas stick to its surface. Write the equation for this reaction. Mg solid plus 2H2O liquid gives MgOH twice aqueous plus hydrogen gas. For the metals that did not react with hot water, arrange the apparatus as shown and observe the reaction with steam. Metals like aluminium, iron and zinc do not react either with cold or hot water, but they react with steam to form metal oxide and hydrogen. 2Al plus 3H2O gives Al2O3 plus 3H2. 3Fe plus 4H2O gives Fe3O4 plus 4H2. Metals like gold, silver and copper do not react with water at all. Now let us see how metals react with acids. Metals react with acids to give salt and hydrogen gas. But do all metals react in the same manner? Let us find out. Activity. Take the metal samples of iron, zinc, aluminium, copper, magnesium, etc. in separate test tubes. Add dilute hydrochloric acid in each of them. Now observe the formation of bubbles carefully. Which metals reacted vigorously with dilute hydrochloric acid? Magnesium, aluminium, zinc and iron react vigorously. Rate of formation of bubbles reduces in order like aluminium, zinc, then iron. Metals react with dilute hydrochloric acid to form metal chloride and hydrogen gas. In the above activity, the rate of formation of bubbles was fastest in case of magnesium. The reactivity decreases in the order magnesium is more reactive than aluminium, more reactive than zinc, more reactive than iron. Mg plus 2HCl gives MgCl2 plus H2. 2Al plus 6HCl gives 2AlCl3 plus 3H2. Fe plus 2HCl gives FeCl2 plus H2. Zn plus 2HCl gives ZnCl2 plus H2. No bubbles are seen in case of copper. This shows that copper does not react with dilute hydrochloric acid. Metals also react with sulfuric acid to form metals sulfate and hydrogen gas. Fe plus H2SO4 gives FeSO4 plus H2. Zn plus H2SO4 gives ZnSO4 plus H2. Mg plus H2SO4 gives MgSO4 plus H2. Reaction with nitric acid. Hydrogen gas is not evolved when a metal reacts with nitric acid, as it is a strong oxidizing agent. It oxidizes the hydrogen produced to water and itself gets reduced to any of the nitrogen oxides N2O, NO, NO2. But magnesium and manganese react with dilute HNO3 to evolve hydrogen gas. Look at this table. It summarizes the reaction of metals with air, water and acids. Let us look at the reactions of metals with solutions of other metal salts. Let us look at one activity. Take a clean copper wire and an iron nail. Put the copper wire in a solution of magnesium chloride and an iron nail in the solution of copper sulfate. Record your observation after some time. The iron nail gets coated with a reddish-brown color of copper and the blue color of copper sulfate solution fades out. In this reaction, more reactive iron has displaced copper, which is less reactive from the copper sulfate solution. This reaction is known as displacement reaction. Give the balanced chemical equation for the above reaction. CuSO4 plus Fe gives FeSO4 plus Cu. There is no change seen in the copper wire. Why? Copper is less reactive than magnesium, so it cannot displace magnesium. A more reactive metal can displace a less active metal from its compound in a solution. Metal A plus salt solution B gives salt solution A plus metal B. Now let us see how metals react with non-metals. We have seen the reactions of metals with number of reagents. Also, the reactivity differs with different metals. Why do metals react in this manner? The reactivity of different metals are different. Do noble gases react? Why? They do not react. They are chemically inactive. Let us look at the electronic configuration of metals and non-metals. It will help us to understand the reactivity of different elements and formation of different compounds. We have learnt that noble gases have a completely filled valenced shell, hence are chemically inactive. Sodium is a silver-colored metal that reacts so violently with water that flames are produced due to formation of hydrogen gas. Chlorine, a non-metal, is a greenish-colored gas which is so poisonous that it was used as a weapon in World War I. When chemically bonded together, these two dangerous substances form a compound, sodium chloride, so safe that we eat it every day. Let us see formation of sodium chloride. We know that sodium atom has one electron in its outermost shell. If it loses one electron from its M shell, then its L shell becomes the outermost shell to acquire a stable octet. The nucleus of this atom still has 11 protons, but the number of electrons has become 10. So there is a net positive charge giving us a sodium cation Na+. On the other hand, chlorine has 7 electrons in its outermost shell and requires one more electron to complete its octet. Thus, the electron lost by sodium is taken up by chlorine. After gaining one electron, its K, L and M shells have altogether 18 electrons, but the nucleus still has 17 protons. This leads to the formation of chloride anion Cl-. Both these elements have a give and take relation between them. Sodium and chloride ions, being oppositely charged, attract each other and are held by strong electrostatic forces of attraction to exist as sodium chloride NaCl, resulting in formation of an electrovalent bond or an ionic bond. It should be noted that sodium chloride exists as aggregates of oppositely charged ions in definite geometrical shape as shown. Thus, the bonds which are formed by such a give and take of electrons are called as ionic or electrovalent bonds. The compounds formed in this manner by the transfer of electrons from a metal to a non-metal are known as ionic compounds or electrovalent compounds. Similarly, the chemical compound that is formed by mutual sharing of one or more pairs of electrons between the two combining atoms is called a covalent compound. Example, water, HCl, etc. Properties of ionic compounds. To learn about the properties of ionic compounds, let us perform the following activity. Take samples of sodium chloride, potassium iodide, barium chloride and observe. What is the physical state of these salts? Solids. Take a small amount of a sample on a metal spatula and heat directly on the flame. Also, try to dissolve the samples in water, petrol and kerosene. Are they soluble? Samples are soluble in water and insoluble in solvents such as kerosene and petrol. Prepare an electrolytic cell by connecting the carbon electrodes to the positive and negative of the battery cell. Also, connect a bulb in the circuit as shown. Put the electrodes into the salt solution electrolyte of one salt. What do you observe? The bulb glows. General properties of ionic compounds are: ionic compounds are solids and hard due to strong force of attraction between positive and negative ions. They are generally brittle and break into pieces when pressure is applied. Ionic compounds have high melting and boiling points, as a considerable amount of energy is required to break the strong intermolecular attraction. They are generally soluble in water and insoluble in solvents such as kerosene, petrol, etc. Ionic compounds in the solid state do not conduct electricity because the movement of ions in the solid state is not possible due to their rigid structure, but they conduct electricity in the molten state. The conduction of electricity through a solution involves the movement of charged particles. A solution of an ionic compound in water contains ions which move to the opposite electrodes when electricity is passed through the solution. Let us move to the next topic, occurrence of metals. Metals occur in nature in the free as well as in the combined states. The most unreactive metals, that is, which are not affected by air and water, example silver, gold and platinum, are generally found in free or native state. Most metals, however, are found in combined state in the form of their oxide ores, carbonate ores or sulfide ores, etc. The naturally occurring compounds of metals, along with other impurities, are known as minerals. The minerals from which metals are extracted profitably and conveniently are called as ores. Ores contain metal compounds with some of the impurities like soil, sand, rocky material, etc. These impurities are called as gangue. Metals can be extracted from the ores by employing different separation techniques. The process used for extraction of metals in their pure form from their ores is called metallurgy. Let us first understand the activity series and related metallurgy before we study the extraction of metals. You have learnt how the reactivity of elements differ for different metals. The arrangement of metals in the decreasing order of their reactivity in the form of series is called the reactivity series of the metals. Thus, the most reactive metal is potassium and is placed in the top of the list, and least reactive metal is gold, which is placed at the bottom of the list. On the basis of reactivity, we can group the metals into following three categories: metals of high reactivity, metals of medium reactivity, metals of low reactivity. Let us look at the extraction of metals of high reactivity. The metals high up in the reactivity series are very reactive like sodium, potassium, calcium, aluminium and magnesium. These metals are obtained by electrolytic reduction. For example, sodium, magnesium and calcium are obtained by electrolysis of their molten chlorides. The metals are deposited at the cathode, which is negatively charged electrode, whereas chlorine is liberated at the anode, which is positively charged electrode. The reaction of sodium is as follows. At cathode, Na plus E minus gives Na. At anode, 2Cl minus gives Cl2 plus 2E minus. Similarly, aluminium is obtained by the electrolytic reduction of aluminium oxide. Extraction of aluminium. Symbol of aluminium is Al. Its color is silvery white. Atomic number is 13. Electronic configuration is 283 and valency is 3. Aluminium is a reactive metal and so does not occur in free state in nature. Aluminium is extracted from its main ore, bauxite, Al2O3H2O. It contains 30% to 70% Al2O3 and the remaining portion is gangue made of sand, silica, SiO2, iron oxide, Fe2O3, etc. Let us see extraction of aluminium. It involves two steps. 1. Concentration of ore, that is, conversion of bauxite into alumina by Bayer's process. 2. Electrolytic reduction of pure alumina. Step 1. Concentration of bauxite. Crude bauxite contains impurities like iron oxide, Fe2O3, and silica, SiO2. These impurities are removed by Bayer's process. In this process, the ore is first crushed and then treated with hot concentrated caustic soda, NaOH solution under high pressure for 2 to 8 hours at 140 degrees Celsius to 150 degrees Celsius in a tank called digester. Aluminium oxide, being amphoteric in nature, dissolves in aqueous sodium hydroxide to form water-soluble sodium aluminate. Al2O3 plus 2NaOH gives 2NaAlO2 plus H2O. The iron oxide in the gangue does not dissolve in aqueous sodium hydroxide and is removed by filtration. However, silica from the gangue dissolves in aqueous sodium hydroxide, forming water-soluble sodium silicate. Diluting sodium aluminate with water and then cooling to 50 degrees Celsius, it is hydrolyzed to give aluminium hydroxide as a precipitate. NaAlO2 plus 2H2O gives NaOH plus AlOH thrice. The precipitate is filtered, washed, dried and ignited at 1000 degrees Celsius to get alumina Al2O3. 2AlOH thrice when heated at 1000 degrees Celsius gives Al2O3 plus 3H2O. Step 2. Electrolytic reduction of alumina. In this process, a molten mixture of pure alumina whose melting point is less than 2000 degrees Celsius is electrolyzed in a steel tank. This tank is lined inside with carbon, graphite, which acts as a cathode, and a set of carbon graphite rods dipped in the molten electrolyte act as anode. Cryolite and fluorspar is also added to the mixture to reduce the melting point to about 1000 degrees Celsius. On passing the current, aluminium is formed at the cathode. The molten aluminium, being heavier than the electrolyte used, sinks to the bottom of the tank, from where it is removed periodically. On the other hand, oxygen is liberated at the anode. The electrode reactions are shown below. At anode, 2O2 minus 4E minus gives O2. At cathode, Al3 plus 3 minus gives Al. The oxygen gas liberated reacts with carbon anode and forms carbon dioxide. As the anode gets oxidized during the electrolysis of alumina, it has to be replaced from time to time. Extraction of metals of medium reactivity. The metals in the middle of activity series, such as iron, zinc, lead, copper, etc., are moderately reactive. These are usually present as sulfides or carbonates in nature. It is easier to obtain a metal from its oxide as compared to its sulfides and carbonates. The sulfide ores are first converted into oxides by heating strongly in excess of air. This process is known as roasting. The carbonate ores are changed into oxides by heating strongly in limited air. This process is known as calcination. The chemical reaction that takes place during roasting and calcination of zinc ores is as follows. Roasting. 2ZnS plus 3O2 gives 2ZnO plus 2SO2. Calcination. ZnCO3 gives ZnO plus CO2. This zinc oxide is then reduced to zinc by using a suitable reducing agent such as carbon. ZnO plus C gives Zn plus CO. Besides using carbon to reduce metal oxides to metals, highly reactive metals like sodium, calcium, aluminium, etc. are also used as reducing agents because they can displace the metal of lower reactivity from their compounds. Example, when manganese dioxide is heated with aluminium powder, the following reaction takes place. 3MnO2 plus 4Al gives 3Mn plus 2Al2O3 plus heat. Can you identify the substances that are oxidized and reduced? MnO2 is reduced to Mn and Al is oxidized to Al2O3. The amount of heat evolved in such reactions is so large that the metals are produced in the molten state. Another example of this type of reaction is the thermal reaction in which iron oxide reacts with aluminium to give iron and aluminium oxide, evolving lot of heat. Fe2O3 plus 2Al gives 2Fe plus Al2O3 plus heat. Let us see how metals of low reactivity are extracted. The metals at the bottom of the activity series are least reactive. They are often found in free state, example, gold, silver and copper. But copper and silver are also found in combined state as their sulfide or oxide ores. For example, copper, which is found as Cu2S in nature, can be obtained from its ore by just heating in air. 2Cu2S plus 3O2 when heated gives 2Cu2O plus 2SO2. 2Cu2O plus Cu2S when heated gives 6Cu plus SO2. Similarly, cinnabar HGS is an ore of mercury. When it is heated in air, it is first converted into mercuric oxide HgO. Mercuric oxide is then reduced to mercury on further heating. 2HGS plus 3O2 when heated gives 2HGO plus 2SO2 gas is evolved. 2HGO when heated gives 2Hg plus O2. How are metals refined? Let us see. The metals produced by various reduction processes described above are not very pure. They contain impurities which should be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining. Corrosion of metals. Corrosion is degradation of materials due to a reaction with its environment. The major problem of corrosion occurs with iron since it is used as a structural material in constructions, bridges, shipbuilding, automobile, etc. Have you ever observed old iron grills in the buildings? Copper vessels which are not cleaned for a long time? Silver ornaments or idols which are kept exposed to air for a long time? Old worn-out cars? Iron reacts with moist air to acquire a coating of brown flaky substance called rust. Copper reacts with moist carbon dioxide with air and slowly loses its shine to gain a green coat of copper carbonate. Silver articles become black after some time when exposed to air because it reacts with sulfur in the air to form a coating of silver sulfide. Aluminium undergoes an oxidation reaction, forming a thin layer of aluminium oxide, forming a barrier to oxygen and water, preventing further oxidation, and becomes resistant to further corrosion. This resistance can be improved by making the oxide layer thicker as done in anodizing. How to prevent corrosion? Corrosion of metals can be prevented if the contact between metal and air is cut off. This is done in a number of ways. Some of the methods are given below. Corrosion can be prevented if the metal is coated with something which does not allow moisture and oxygen to react with it. Coating of metals with paint, oil, grease or varnish prevents the corrosion of metals. Example, rusting of iron can be prevented by this method. Coating of corrosive metals with non-corrosive metals also prevents corrosion. Let us see some of the methods by which metals can be coated with non-corrosive metals. Galvanizing. It is a process of giving a thin coating of zinc on iron or steel to protect them from corrosion. Example, shiny iron nails, pins, etc. Tinning. It is the process of giving a coating of tin which is molten tin over another metal. Example, cooking vessels made of copper and brass get a greenish coating due to corrosion. This greenish coating is poisonous. Therefore, they are given a coating of tin to prevent corrosion. Example, kadai. Electroplating. In this method, a metal is covered with another metal using electrolysis. Silver-plated spoons, gold-plated jewelry, etc. are electroplated. Anodizing. In this method, metals like copper and aluminium are electrically coated with a thin, strong film of their oxides. This film protects the metals from corrosion. We have discussed the anodizing technique in detail earlier. Alloying. An alloy is a homogeneous mixture of two or more metals or a metal and a non-metal in definite proportion. The resultant metals, called alloys, do not corrode easily. Example, stainless steel, brass, alloy of copper and zinc, bronze, alloy of copper and tin, stainless steel alloy, iron, nickel and chromium. If one of the metals is mercury, then the alloy is known as an amalgam. Pure gold, known as 24-karat gold, is very soft. It is therefore not suitable for making jewelry. It is alloyed with either silver or copper to make it hard. Generally, in India, 22-karat gold is used for making ornaments. It means that 22 parts of pure gold is alloyed with 2 parts of either copper or silver. Well, that ends the chapter. Hope it was a joyful learning. You have the options to view a mind map for a quick recap and a question and answer section to study the exercises. Wish you all the best. Bye till we meet again.